So this is the first in a series of some review videos that cover material from MEMS 1041. In this lecture we will discuss population and sample statistics and then illustrate how to analyze the data using both Excel and Matlab. So first let's review some fundamental statistics concepts. Let's assume that the data you see on the plot here is being acquired from some sensor. And it's important to realize that even if the signal we're measuring is perfectly static in nature, meaning it's not changing at all, the actual data we get from the sensor itself is always going to have some amount of noise associated with it. So our task is to quantify that noise, and one way to do that is to look at how the data is distributed. So we could take all this data, organize it into the histogram like you see here, and we would recognize the distribution as what's called a normal or Gaussian distribution. Now this is important because a lot of the tools that we use are based on the assumption that the underlying data is indeed normally distributed. So when the data follows a normal distribution, the result can be quantified using two variables. The first is the average or the mean value. The normal distribution is always symmetric about this mean value. The second is the variance, or its square root, the standard deviation, which then quantifies the spread of the data. Now the curve that defines the distribution is called the probability density function, or PDF. The curve that you see here is of course a normal PDF, meaning it defines a normal distribution, but every other type of distribution has its own unique PDF as well. One attribute that they all have in common, though, is that the integral of the entire curve is always going to be equal to 1. And what this does is it gives us the ability to then analyze different slices of the distribution and express the integral of that slice as a percentage of the data that falls within its bounds. So another function that you're probably not quite as familiar with is the cumulative distribution function, or the CDF. And this is a way to evaluate the integral of the PDF. To find those areas underneath the curve, we can simply evaluate the CDF at different x values. So the output of the CDF is the area underneath the PDF from the leftmost bound of the distribution, and for a normal distribution this is obviously negative infinity, to some specified x value. So in MEMS 1041, when you were finding areas underneath the distribution, you would typically calculate a z-value and then go to a table and look up what the corresponding area would be. As an example, if z were found to be 0.45, you would locate the z equals 0.4 row and then the 0.05 column for the second decimal place to find a value of 0.1736, which means that 17.36% of the data lies between z equals 0 and z equals 0.45. In reality, what the z-value represents is the number of standard deviations away from the mean value. So z equals 1 means 1 standard deviation away from the mean, and so on for z equals 2, 3, etc. So the z-value is actually defined all the way to positive and negative infinity, but we typically don't see too much beyond z equals 3, because at that point, once you are 3 standard deviations away from the mean, there's really not much of the curve left, only a very small percentage of the data. So for instance, looking at the bottom right corner where z equals 2.99, this corresponds to an area of 0.4986, or nearly 0.5, which is half the total area, a value that we would indeed find as z approaches infinity. So as mentioned before, another way to express the area under the curve is in terms of the CDF. For the slice shown in the upper left figure, we could also calculate this as the difference between the CDF evaluated at the same z value and the CDF evaluated at 0. So for this example, we could also recognize that the CDF of 0 is exactly half the distribution, or in other words equal to 0.5. So for large amounts of data, it's actually better to make use of the CDF, because you won't need to calculate a z-value and then use the table each and every time you need to find an area. You can simply include the analysis within an Excel spreadsheet or a few very simple lines of code in Matlab. So let's take a look at a quick example. In example 1, we are analyzing the height of 25-year-old males in the United States. The average is 70 inches with a standard deviation of 3.5, and we want to use Matlab and Excel to first find the percentage of data that lies between 68 and 76 inches, and then the bounds within which 90% of the data would lie. So in part A, we are simply looking at the normal distribution. We have 70 as the mean, and we want to find the area between 70 and 76, and then the area between 68 and 70, and then we would simply add those two for the total percentage between the two bounds. In terms of the CDF, we would simply evaluate the CDF at 76, and from that subtract the CDF evaluated at 68. And what remains is the slice of the distribution representing the area of interest. So instead of looking up two separate z-values and using the tables, the CDF enables easy implementation into Excel and Matlab. So in Part B, we are actually doing the opposite of what was done in Part A. In this case, we don't know the actual x values, but we do know that the area between the two bounds needs to be 0.9 or 90%. So the challenge is to find a z-value such that the area between 70 and x2 and then the area between x1 and 70 are both equal to 0.45. Because this is symmetric about the mean, we can express x1 and x2 as the mean value plus or minus z multiplied by the standard deviation. In order to express this problem in terms of the CDF, it's important to realize that if the area between the bounds is 0.9, then the area outside the bounds must consist of 0.05 to the right of the interval and another 0.05 to the left of the interval. So the problem can be thought of as first finding x1 such that the CDF of x1 is 0.05, and then finding x2 such that the CDF of x2 is 0.95. So let's go through both Part A and Part B, first in Excel and then in Matlab. So if we were able to sample the entire population, we would know the true mean and the true variance, which are then used to define the distribution. For most engineering applications, though, we cannot realistically sample the entire population, and we are forced to deal with a smaller portion of it. For this small sample size, we could calculate the sample mean and the sample variance, but both could be slightly different than their population counterparts, resulting in a slightly different distribution. We could simply assume that the sample statistics are a good approximation of the population statistics, but we really want to do better than that. We want to be able to take the sample mean and place bounds of uncertainty around it, such that we are confident that the true mean lies somewhere within those bounds. Now it stands to reason that as we increase the number of samples, the mean and variance will approach the population values, and the uncertainty would decrease. Now with this in mind, let's now explore the t-distribution, which is what we use for small sample size analysis. So when we talk about the z-distribution, we are inferring that the population statistics, in other words the mean and variance, are known with absolute certainty. In order to achieve this, we would again have to sample the entire population, not a very realistic approach. As previously noted, the more samples we take, the more reliable the estimates become in quantifying the population or true statistics, and a quantity known as the degrees of freedom is what accounts for this fact. In this situation, it is simply equal to the number of samples minus 1. In order to make any statistically sound conclusion for any type of analysis, the degrees of freedom must be greater than 0. So think of the mean or the standard deviation. These only make sense when there are at least 2 samples. In other words, the degrees of freedom equal to 1. Now, a distribution with only 1 degree of freedom is shown here, and we call this the t-distribution. It is similar to the z-distribution in that it is symmetric about the mean value at t equals 0. And as t approaches positive or negative infinity, the PDF curve approaches 0, also the same as the z-distribution. Another common trait which may or may not be readily apparent from this graph is the fact that the total area under the curve for the t-distribution is equal to 1. Changing the number of degrees of freedom results in a new t-distribution, but the same common traits exist, namely the curve is symmetric with a total area of 1. So as the number of samples becomes very large, the t-distribution and the z-distribution become one and the same. So the take-home message is this, that all the analysis tools using the z-statistic are the same when using small sample sizes, except the z-value is now replaced by the t-value. Now the only nuance is the fact that we now must also specify the number of degrees of freedom. Note that the definition of the z is the number of standard deviations away from the mean using x prime, the population mean, and sigma, the population standard deviation. The t-value is the exact same definition, only in terms of the sample mean x bar and the sample standard deviation s sub x. So for any sample data, we also want to be able to confidently place bounds on the sample mean to create an uncertainty interval for the true mean. This uncertainty is defined as the product of t and s sub x bar, which is known as the standard deviation of the means, and is equal to the sample standard deviation, s sub x, divided by the square root of n. So as the number of samples increases to infinity, this uncertainty approaches 0, suggesting we are more and more confident of the true mean value. So in example 2, we are going to reanalyze the data from example 1, only we are going to assume this comes from some finite sample size with the number of samples n being equal to 20. In addition to that, we are going to find the bounds to which 95% of the data lie. Note that in part B we did the same thing, only we determined these bounds for 90% of the data instead of 95. And in part D we want to find the true mean using 95% confidence. Now, the purpose of C and D in this case is simply to illustrate the fact that these are two different problems. If you want to find the range in which 95% of the data lies, and if you want to find the true mean with 95% confidence, the analysis is going to be slightly different. So in part A, we will approach it the same as we did in example 1, only now we need to account for the fact that the distribution is a t instead of a z distribution. So we will need to specify the number of degrees of freedom. The approach in part B is also similar to that used in example 1. We need to find x1 and x2 such that the area between them is going to be equal to 90% or 0.9. For this, we're simply going to take our population statistics and replace them with our sample statistics. So we replace x prime with x bar, and we replace the product of z and sigma with the product of t and the sample standard deviation. And part C is basically the same as part B, only we are changing the area from 0.9 to 0.95. And finally, for part D, we are trying to find the true mean using 95% confidence, the solution of which looks similar to that of part B and C, except now the standard deviation is divided by the number of samples. Again, this is called the standard deviation of the means. So let's solve these problems first in Excel and then in Matlab. So in summary, there are a number of functions both in Excel and Matlab that make analyzing the data very easy to do behind the scenes and even automatically. There are 3 distributions in particular that we've discussed. The first is the normal distribution, the second is the z distribution, and the third is the t distribution. There are different functions that analyze either the PDF or the CDF or help with the inverse of that when we are dealing with the known percentages and we want to find the corresponding x value or z value or t value. In Excel, to get the PDF or CDF, it is the same function. We just change the last input, the last argument, from false to true. This is also the case when using the z and the t distributions. Keep in mind that the z distribution is simply the normal distribution, taking the mean to be 0 and the standard deviation to be equal to 1. With the t distribution, it's the same concept with the other distributions. There's just an additional input or argument to that function, namely the degrees of freedom. In Matlab, we have similar functions. In this case, the PDF and CDF are found from different functions instead of being built into the same function. But the concept is the same, and for the t distribution, again, we need that extra input. For the interested student, you can also explore 3 additional functions in Matlab, PDF, CDF, and ICDF, which perform the same functions, but you can then specify one of many different distributions. So with the same function, you could analyze as if it were a normal distribution, a t distribution, a chi-squared distribution, binomial distribution, so on and so forth. So homework has been posted associated with this lecture and will be due at the end of our next lecture. So you are encouraged to not only look at those beforehand but attempt to complete them. And we will spend time in class going over issues you might be having.